welcome back. In this video, we are going to be talking about differential rate law with kinetics. So basically what our rate laws are, they actually describe our reaction rates mathematically. So important things to note with rate laws is that we always assume that only the forward reaction is important. So in our reactions turn into products, but at the same time, some of our products are turning back into reactants. So when we're talking about rate laws, we're only going to assume that our forward reaction is important. So what that means for us with our rate laws is that they are only going to contain reactant concentrations. We have two different forms. We have the differential rate law and the integrated rate law. So the differential rate law shows how rate depends on concentration, just called rate law occasionally, and then integrated shows how concentration depends on time. And really the only difference between them is, the only reason you'd choose one over the other is it depends on what kind of data you can collect easily. So either one is fine. And once you have one type, you can always calculate the other. So today in this class, we're really just going to focus on our differential rate law, and we'll talk about the integrated rate law in 2 class periods from now. All right, so let's jump in. So if I have the basic reaction, little a, capital A right here, you guys can read right there. All right, if I have that basic reaction, then my rate is equal to K, and we'll talk about K, times concentration of A to some power times concentration of B to some power. And then concentration of A and B would, of course, be our molarity in moles per liter. Now, this M and this N are going to represent positive or negative integers or fraction. Most of the time, they are positive integers, and they're going to be relatively small whole numbers. Most of the time, it's either 0, 1, or 2. In this. Now, K is our specific rate constant. And this value has many factors that it depends on. It depends on the reaction, the temperature, if there's a catalyst or not, all of those things. But the faster the reaction, the larger your K value. Now then, I kind of said our exponents are positive whole integers. The exponents basically tell us the order of our reactants. And then the sum of our exponents is the overall order of the reaction. So for example, right here, if I have R equals K times concentration of A, and we don't have anything written there, so we can assume it's 1, times concentration of B squared, A would be first order because its exponent is 1, and then B would be second order. 1 plus 2 be our overall order. So overall, we'd have a third order because 1 and 2 adds up to 3. The other thing is we can calculate our units of K based on our reaction orders and our units of concentration. So we will be solving for K as well once we actually have data values. And there's kind of some information. So like if our rate is in moles per liters per second in the above rate law, we could find the units for K by plugging them in and simplifying them to get our units there. Now then, down here, we do have a shortcut to determine the units for K. So if when we're doing this and we're actually solving and doing the math for units of K and you're like, I'm not positive what's going on here, that's okay. This is a little shortcut. So K is equal to liters to whatever power divided by moles to whatever power times time. And the value of that power will be 1 less than the overall order of the reactions. Like if you have a third order reaction, be liters squared divided by moles squared times time, whatever your time value is. So it's always going to be 1 less than the order of our reaction. So hopefully that's helpful and a helpful little shortcut for determining the units of K for you. All right, so let's talk about determining the differential rate law from experimental data. And I'm going to show you guys 2 methods. The first is just analyzing our data. And then the second is still analyzing our data, but it's just a mathematical approach. So one of them is really great if your data is very straightforward and easy to read. And then the other one would be more useful if maybe we have slightly more confusing data or our data isn't as straightforward as it seems. So If we double our initial concentration of a reactant, and that causes the initial rate to double, then our reaction is first order. If we double the initial concentration of a reactant, and that causes our initial rate to quadruple, then our reaction is second order. If doubling the initial rate of a reactant does not change, so we have like no change in our initial rate, then the reaction is zero order. So we're going to have to do a lot of data analysis here to see how is my rate changing based on how my concentration is changing. So these are like relatively easy. We kind of have the same general form for every single one of these reactions. So let's kind of jump in and start analyzing our data here. All right, so I'm going to move in to problem one right here. And there's just a couple things you need to look at is you kind of need to see where's my rate changing, where's my concentration changing, and where's it staying the same, and how can I compare these? So for example, in this one, on our first one, as we move from trial 1 to trial 2 for A, we have no change in our reaction. No change in our reaction. Now then, for B, as we move from trial 1 to trial 2, our concentration doubles because I have 0.2 in trial 1 and 0.4 in trial 2. So my concentration doubles of B. And so how does that affect our rate? Well, our rate doubled. So since our concentration doubled and our rate doubled, that means that B is going to be first order. Since as B's rate doubled, as B's concentration doubled, so did our rate. All right. So then in our second and third trial, between our second and third trial, the concentration of A doubled while the concentration of B stayed the same. We have no change. And we went from 0.02 to 0.08. So we have a times 4 there. So that means that A is second order because as my concentration of A doubled, so did my rate quadrupled. Sorry, didn't double, it quadrupled. So that would be a second order. So then we can write our rate. And our rate follows the same general form. We always have our rate constant K, concentration of A to its order. And so since A is second order, the concentration of A squared times concentration of B to its order. And since B is first order, we don't have to write it, and ones are assumed. So A is second order, B is first order. So our overall reaction order is going to be 3 because 2 and 1 would add up to 3 as our total overall reaction order. Okay? So that would be our rate law for our first one. Rate is equal to our rate constant times concentration of A squared times concentration of B. All right, let's look at our second one now. So once again, we still need to look at how our data values are changing from trial to trial. So from trial 1 to trial 2, as my concentration of A, it's going to double. And there's no change to my concentration of B from trial 1 to trial 2, and my rate doubled. So I can see that A is going to be first order here because as my concentration doubled, so did my rate. So now let's look at this next part. So then this next one, as I move from trial 2 to trial 3, my concentration of A doubled. So we should already be thinking about what does that mean for our rate. My concentration of A doubled there, then my rate should double as well. But my concentration of B also doubled. So then what happens to our rate? Well, our rate doubled. So if my concentration of A doubled and A is first order, I've already figured that out, then my rate should have doubled. So that means that makes sense for trial A. But B also doubled, and there's no other effect than just the doubling there. So that means that B actually had no effect on it. So B is going to be a 0 order here. because we see that since our concentration of A doubled and our rate doubled, well, we already knew A was first order and it would affect it. And that's the only change we see is the change from the concentration in A. Okay, so then my rate is going to be K times the concentration of A to the first power, and then it would be B to the 0 power. Now, anytime we have anything raised to the 0 power, it's just 1. So we don't need to include that in our rate law. So it would just be K times concentration of A. And so our overall reaction order here would be 1. Okay, so I want you guys to go ahead and try to do the next two. They are a little bit trickier just because we do have some scientific notation, but I want you guys to try to do them and then pause your video and come back and check your answers. All right, so pause your video now. Okay, guys, so hopefully you completed those. So for our first one, we see that our concentration of A doubles from trial 1 to trial 2. And as that happens, our rate is going to quadruple. And then same thing here from trial 2 to trial 3, our rate doubles and our rate quadruples once again. So we get that our rate is equal to K times concentration of A squared because A is going to be second order. And then for our problem number 4, we have as our concentration of A doubles, our B doesn't change, and our rate doesn't change. So A is going to be a 0 order. And then A doesn't change from trial 2 to trial 3. B doubles, and our rate doubles. So rate is equal to our K value, our constant, rate constant, times the concentration of B to the first power. Once again, we don't have to write that. All right. So let's do one more together before I show you guys a slightly different way of solving the order of reactions, the math way. So you guys can choose either one, but I'm going to do one more with this method before we move into doing the math. All right. So right here, we have our experiment here. So from in trial 1, we kind of have to analyze our data a little bit. Okay, come on. All right, there we go. So as I go from experiment 1 to experiment 2, I have no change in my concentration of NH4. But I doubled, I'm going to have to write it on this side since I don't have enough space, my concentration of NO2. And that also caused my rate to double. All right, so we can already see that NO2 is going to be first order. All right, so then from trial 2 to trial 3, I have times 2. I've doubled my concentration of NH4, and I have no change on my concentration of NO2. And once again, my rate did double there. So that means that these are both going to be first order. So rate is going to be equal to our rate constant times the concentration of NH4 to the first power, which we don't have to write because it's 1, so it's just assumed, times the concentration of NO2 to the first power as well. All right, so now this question says determine the value of K and its units. All right, guys, so we have our rate law here. So we're actually going to use our data and plug our data in to solve for our rate constant. So if I want to solve for K, K is going to be equal to my rate divided by the concentration of NH4 times the concentration of NO2, -1. So now I'm just going to pick any of my trials and plug them in. So I'm just going to plug in trial 1 since that's going to be probably the easiest one to do. I don't know. I just always pick the first one. You can pick any of them and you should get the same answer though. All right, so our rate is going to be 1.35 times 10 to the -7th, and that is in units of moles per liter per minute. divided by our concentration of ammonia, which is 0.100, and that is in moles per liter, so we have molarity, times our concentration of NO2, and that is 0.005 moles per liter. All right, and then we plug our data values into our calculator, and when I plugged the data values in, I got 3 times 10 to the negative fourth as our rate constant, and then we have to figure out our units. So to figure out our units, we're going to kind of cancel our units here. So I have moles per liter on the top, and I have it on the bottom again. If we're dividing by something we're dividing by, it comes to the top, so I end up with liters over moles times minutes as my units for K. So 3 times 10 to the negative fourth liters over moles times minutes. Okay, so now for this next part, I'm going to show you guys how we can determine order using math. And you really can use either method. It just depends. Sometimes if our data values aren't super straightforward, sometimes it's easier to use the math versus the method that we talked about of if A doubles and this doubles, it's first order. Sometimes this is just a little easier if your data values aren't as straightforward as they have been for us so far. All right, so we'll look at how to do that. So this one says determine the rate law and justify your answer. So I'm going to show you guys a slightly different way to solve these, just depending on your brain. So to determine the rate law, we do have to determine the order. And so what we're going to do is essentially we're going to compare two rates. So how I do this is I'm going to, I typically like to compare, so we still need to look at our data. And here we see that it basically doubles, not exactly. Then from there to there, it's multiplied by 4. You can see with B that it doubles from trial 1 to 2, but that it stays the same pretty much from trial, 1 to 2 it doubles, but it stays the same pretty much from trial 1 to trial 3. So I need to figure out my order. So I want to look at some data values where they're very similar. So I'm going to look at trial 1 and trial 3 first and compare those rates. All right, so here's what I know. All right, I'm going to compare rate 3 and rate 2. I'm going to zoom in a little bit so it's easier for me to write. And rate 2. And I know that in general, rate 3 is going to be equal to my constant times the concentration of A to some power, and I'm just going to call it X, times the concentration of B to some power. And that's true for rate 2 as well. So rate 2 is going to be equal to the concentration of K times the K times the concentration of A to some power times concentration of B to some power. And we don't exactly know what those powers are yet, but using this method, we're able to do it. So what I did, and the reason I picked these, and sorry, this should be rate 1, not rate 3, is what I'm looking for in my first one is I'm looking to be able to cancel out one of them and just solve for the other. So in this case, I have 2.01 and 2.00. Now, those aren't exactly the same, but they are close enough that we're going to be able to just kind of make some assumptions and assume that we can cancel out, and we may have to finagle our numbers a little bit, but they're close enough in value that we can cancel them out. All right, so now I'm just going to plug in values. So my rate for experiment number 3 is 80 moles per liter per second. And my rate for number 1 is 5 moles per liter per second. That's going to be equal to our rate constant, K, times, and for experiment 3, my concentration of A is 40.2 to the X. We don't know what that is. And my concentration for B is 2.0 to the Y. All right. Then we're also going to plug in rate 1. So again, K times my concentration of A, which is 10.1 to the X, and then 2.01 to the y. Okay, so now we're going to cancel out as many like values as we can. So k was this on top and bottom, so that can cancel out. And I'm going to go ahead and cancel out this 2 and that 2.01. Now, do I know that they are not exactly the same? Yes, I do know that. But for this, I'm just going to make an assumption that they're going to be close enough that I'm still going to be able to get the general gist of what's going on here. All right, and then I'm just going to simplify my reaction. So 80 divided by 5 gives us 16, and then 40.2 to the x divided by 10.1 to the x. Since they have the same exponent, I can divide those, and I get then 3.98 to the x. All right, now 3.98 is extremely close to 4. Remember that I also kind of finagled these numbers a little bit, and so they weren't exactly even. So we can just say it's probably 4. So to get 16, it's 4 to what power? X has to be 2. So that would mean then that A is second order, because that exponent we solved for it, it's going to be 2. Okay? Now then we'll just compare another one. And this time it doesn't matter. You could either use rate 1 and 2 or 2 and 3. You just want to make sure that your B value is changing there. All right. So now we're going to do the same thing for B, but I can actually plug in my A value. So I'm going to compare rate 1 and rate 2 just because it's a little easier. Also, whenever I'm putting them over each other to compare them, I find it a lot easier to put the bigger rate over the smaller rate, just end up with like whole numbers versus decimals, which is easier for me to work with. So that's the way I do it, but you'll get the same answer either way, but I just like working with the bigger numbers. So now then, same comparison. So we're going to compare rate 2 and rate 1. All right, I still know my equations. It's going to be K, concentration of A, and this time it's concentration of A squared, because I do know that it's second order. I figured that out last time, times B, and I don't know the order of B yet, so it's going to be B to the Y. All over the same thing for rate 1. Concentration of A squared, concentration of B to, and I don't know the order on that one. So that's what we're solving for. All right, so let's plug in our values. So for rate 2, once again, we got our rate of 80. Rate 1 would be 5. And then we don't know our K value, but we do know our values for the other ones. So for rate 2, A started out at 19.8 squared times concentration of B for rate 2 would be 3.99 to the Y value. Honestly, the thing I struggle with most on the math here is keeping straight which values I need to plug in on which side. That's I think personally, the hardest part of solving it this way. So then putting rate 1 on the bottom, so concentration of A in experiment 1 is 10.1 squared times concentration of B is going to be 2.01 to the Y. All right, so then once again, gonna kind of cancel out what I can. My A's aren't exactly the same, so I am actually gonna have to do a little bit more algebra. But yeah, cancel out what I can. I can cancel out those K values at very least, and then start simplifying. So 80 over 5 is once again 16, and 16 is then equal to, if I square those out and divide them, I get 3.84 times 1.985 to the x, or to the y. So then I'm just going to simplify a little more, divide both sides by 3.84, and I got 4.1 is equal to 1.8985 to the y. That's basically 4. It's basically 2. So y is going to be equal to 2. So B is going to also be second order. So then after I've solved all of that, I can then do my rate law. So rate is equal to the K value, concentration of A squared times concentration of B squared. Now again, If you just want to look at the data values and look at how is the rate changing, that's totally fine. I just think this method is sometimes a little nice when your changes aren't clear cut. Like in this case, what you may notice is that, A doubles every single time. So it's just a little harder to analyze our data that way, which is where this method comes in handy. Or if you like math and you like doing math, this method's great because a lot of times on the AP problems, they ask, for you to solve this problem. But then, while solving it, they also ask you to justify. And if you do the math part, like if you do the math like this, that is your justification, is solving for it instead of, whereas if you don't do the math, you actually have to have a justification of where you got those answers from. So up to you, either method's fine. I'm going to solve one more using this method with you guys, and then I'm going to have you guys solve the last two on your own. Okay, but let's go ahead and answer the last part of this question. So it says to determine the value of K and its units. So just like last time, we're going to kind of manipulate our rate equation to solve for K. So in this case, K is going to be equal to our rate divided by concentration of A squared times concentration of B squared. All right, and so since we have that, now we just plug in data values. I normally always just plug in trial one just because I feel like typically it seems like trial one is going to be our shortest trial or our smallest values to work with. And so, I don't know, I just like to plug in trial one. So that's what I'm going to plug in here. So my rate in trial one is 5 moles, and because it also says units, we have to solve for our units too. Moles over liters times seconds times concentration of A. So A would be 10.1 moles per liter squared, and times concentration of B, which is 2.01 moles per liter squared. Okay, so after we plug it all in, we're just going to kind of simplify down. So I'm going to go ahead and square out everything, all that fun stuff. So when I square it out, I end up with 5 moles per liter times seconds over 10.01 squared is 1,021 moles squared over liters squared times 4.0, what did I write there? I can't read my handwriting. 4.0401 moles squared over liters squared. And then kind of start simplifying my units up here. So since I have moles and liters on the top and I have it on the bottom, that's going to cancel out one of them. Anytime we are dividing by something that we're dividing by, it's going to flip over to the top. So plug all your numbers on into the calculator. So 5 divided by 1,021 times 4.0401. And I ended up getting 1 sig fig here, 0.01 as my units here. As my rate, my K. And that'll be liters to the liters cubed over moles cubed times seconds. So that'll be our K value. Okay, let's do one more together. All right, and then I'm going to leave you guys to do the last ones. All right, so I am going to do that problem the way I just showed you guys one more time. But for you guys, you can solve it. If you don't want to do it that way, you're welcome to go ahead and just pause the video, solve it the way you want to, and then kind of check back with me. So here we go. So once again, kind of need to look at our data. So from trial 1 to trial 2, does not double. No change there. So yeah, no change. And the concentration of B does double. And then from trial 2 to trial 3, A is going to double, and there's no change on B. So we can actually kind of see the rates that we need to compare in order to figure it out. So I'm going to compare trial 1 and trial 2 to figure out B, and then trial 2 and trial 3 to figure out A. So let's jump in with our first one. So let's compare. I'm just going to start with B since that's trial 1 and trial 2. So the rate of our second experiment over the rate of our first experiment is going to be equal to our general rate law is going to be K times A to some power times the concentration of B to some power, which is going to be our general equation, even though we don't know what our order is at this point. You guys will see this one's actually going to be much easier to solve because we don't have to make any like guesstimates or anything like that. So here we go. So I'm going to plug in my values. So my rate 2 for my second experiment is 20. And my rate for my first experiment is 5. So I end up with K times, and in my second experiment, the rate of A is 3 to the X. And then the rate of B is 4 to the Y. And then plug in our values for the first rate as well. K times my rate concentration of A is 3 to the X. And then concentration of B is 2 to the Y. All right, so then we can start canceling out like terms. So K on top and K on bottom will cancel out. And then we have 3 to the X and 3 to the X. And those are the same, so those will cancel out as well. So then when we plug it in, we end up with 20 divided by 5 gives us 4. And then 4 to the Y and 2 to the Y, divide those by each other. We end up getting 2 to the Y. So 4 equals 2 to the Y. So that means Y has to be 2. So our B is going to be second order. All right. And then we're going to do the same thing in comparing rate 3 and rate 2 to figure out A. So rate 3 over rate 2. And once again, I always just do bigger rate over smaller rate because it ends up being a little easier. Goes K, concentration of A to the X, because we don't know its order yet. And then B squared, because we do know its order. Same thing down here. K, A to the X, and then B squared. All right, let's plug in our values. So the rate of 3 is going to be 40 over 20 is equal to, and then we'll just start plugging in our values. So K, and the concentration of A is going to be 6 to the X, and then the concentration of B is 4 squared. And that's our rate for that's experiment 3 data, and now we're going to do experiment 2. So then at K is equal to concentration of 3 to the X all over 4 squared. So once again, we'll cancel out like terms. You guys are probably already seeing that this math is quite a bit easier than the other one. Let's cancel out 4 squared, cancel out our K, and we end up with 40 divided by 20 gives us 2. And so then 3 divided by 6 also gives us 2 to the X. So that means X has to be 1. So A is first order. All right. And then we're going to write our rate law. So our rate law is equal to rate is equal to our rate constant K times concentration of A to the first power times concentration of B to the second order. All right, and then determine the value for K and specify its unit. So once again, we're just going to plug in data values to figure this out. So K is going to be equal to our rate over the concentration of A times the concentration of B squared. And then we'll just go ahead and plug in values. So I, once again, I'm using the first one. So our rate is going to be 5 moles per liter times seconds over, and then our concentration of A for the first data set is 3 moles per liter. And then our concentration for B is going to be 2 moles per liter squared. So you can kind of square that out, cancel out what's going to cancel, all that fun stuff. It's like since I have moles and liters on top, those on the bottom are going to cancel. And then plug in our data values. And I got 0.4 liters squared over moles squared times seconds. All right. So at this point, I want you guys to go ahead and pause the video right now and go through the next two problems, and then we'll quickly go over the answers after we come back. Okay, so pause the video and work through them. All right, let's go over them. So for our first one, I got that A is first order and B is first order. So our rate is equal to K, the rate constant, times the concentration of A times B. And I got that the value of K would be 0.25 liters over moles times seconds. And then for the next problem, I got that A is a zero order and B is a first order. So our rate is equal to K times the concentration of B. And then our K value would be 3, and the units are 1 over seconds. Okay, guys, that's differential rate law. Hopefully you feel pretty good about it. Yeah, all right, that's all I've got for you.